Okay. Okay, guys. So this is our last week of lectures, and yeah, I a little bit updated the work page. So it's our last week. And before we move into this topic, I want to say that I, on the halfway of finishing grading homework 6 on GPT model, and most of you did pretty good job. And in the first part, um, when the question was to make a conversation with um, a famous person, I enjoyed reading your conversations, and also I noticed that some students talk with large language model as with a real person, like complaining about their problems, what I will do after graduation. And it was also fun that the large model, like a real person, just stopped generating tokens on this interesting question because it was the limit of the tokens. So it was fun to observe this kind of Eliza effect. Um, what else? Yeah, I received email from Jason. Uh, um, so I posted two spreadsheets, but I didn't provide the access to these spreadsheets. So now uh, you can uh, uh, fill in these spreadsheets about projects. Okay, and so it's now week. Okay. So now let's talk about this week topic, and it's interesting that we had abbreviation ML for machine learning, LM for large language models, or for language models. Now we will talk about MLLM. So multimodal large language models. Um, and uh, let's see. So last week I mentioned about the change in the um, understanding of different modalities. So there's subtitle on the way to AGI. What does it stand for, AGI? AI, HI. Yes. So what's the difference between AI and HI?
Well, depends on how you define AGI.
Just kind of to mimic a human. So of course it's at least for now not realistic task, but still um, we can combine now different sensors like vision, speech, language, and like in a human being, all the sensors are developed and they help to understand the environment and to learn. The same idea is in combining different modes in models. Um, and if you think about images, in images, we can understand what is the top, what is the bottom. I mean, where's the sky, what is the color, but it's maybe the image domain is not so informative as language domain. So, and on the other reason why language domain is kind of considered now as the main modality that contains the most information about our world is because it's trained on all the texts from internet. So it's also so the much more data than other modalities. And the idea now is to use the information about our world encoded with language models, but also incorporate other modalities like video, audio, visual images, maybe video also, and the multimodal language models can process now different modalities as input, but also they can return also, for example, generate images, not or audio, not only generate the texts. And the to make it work, we need a so-called connector, which maps the other modalities in tokens that language model can understand. So kind of map the other modalities into language modalities. And today I want to talk about vector representation of images. So it's actually also like in this recent couple of years, the paradigm of machine learning has also changed. Like in the classical machine learning, we tried to use features and create models like linear regression. We multiplied just numbers by these features. Nowadays, instead of representing data as features, we represent data by vectors. For example, tokens are represented by vectors. Now I want to talk about images, visual transformer. Images now are also encoded as vectors. Audio also now we use it's called WAV2VEC model, which like Word2VEC, it represents audio as vectors. And we can use this vector representation to generate new images, new text, new audio. So it's kind of like 2 years ago, no, it was 3 years ago when I was in a master degree in audio signal processing at UFR. We didn't hear about these vector representations for audio. We used spectrograms, which is conventional audio signal processing from when this fast Fourier transform was introduced from 60s. And the only way to generate a new audio was to create a spectrogram, like text to speech. Based on the text, the model creates spectrogram and then convert the spectrogram into waveform. Nowadays, we can use a model that, for example, we can pass the audio for a model and take the embeddings, the vector representation from one hidden layer, and use these vectors to generate this audio back to reconstruct. And today we will talk about vector representation of images. And when we have this vector representation, then we can use them as tokens for our large language model, because we will have the same representation and for words and for images and for audio. And so we can treat them equally and use cross attention, for example, between them. So now let's talk about some benchmarks for images. So this is question answering benchmark. Let's see. You can see the bottom line, but maybe it's okay. It's good to see the year. So this is from 2019, where for images, they constructed a graph, and a graph described kind of color, action, and then they built different questions based on this graph. For example, what color is the food on the red object, and so on. So yeah, if you want to, for example, perform image captioning, what are the tasks actually? There are different tasks. For example, you can show an image of, I don't know, for example, a Renaissance painter, and ask who is the painter of this picture. In this case, maybe your model should go to some database or internet and compare this image with some catalogs from museums and to answer this question. Also, you can ask questions like general questions, for example, for Eiffel's Tower. You can use the image of the Eiffel's Tower and ask, for example, which year it was built, or who is the engineer who constructed. So maybe in this case, your language model should also go to internet to answer these questions. But for image captioning task, when you just provide an image and ask the question, what is in this picture, you don't need to go to internet. You train a model that actually was trained on the pairs, images, and texts. So this model can detect the objects on this image, for example. And nowadays, there are very many multimodal models appear. And of course, we need some benchmarks to evaluate these models. And this is one of the benchmarks. So it contains 22 million questions and 100,000 images. The other benchmark uses the school textbooks, and it's pretty old. I believe it's 2016. At that time, they tried to build graphs, but for now, this benchmark is used just as a collection of images and questions. The next benchmark was using the college level textbooks. Let's see, physics, math, and it's kind of tests. And it contains 11,000 questions from 6 disciplines. The other benchmarks, more recent, is called text visual question answering. The interesting fact about this benchmark that evaluation metric here was different in previous benchmarks. It was accuracy. In this benchmark, it was called by the name of the article. So CQA stands for the name of this article of this benchmark. And it's 100% that 3 people answered, for example, classified the object on the picture as the same class, and 30% if only one person kind of indicated this class. The other benchmark is documents. It's another kind of area of research to the optical character recognition, how to recognize text from the paper. And in this case, it's important to use very high resolution for images. So because if we use a low resolution, for example, if we apply just convolution neural networks, and you remember convolution neural networks, they well, first of all, we resize our images in just the input to our model. Do you remember what is the size of input for like classical models like ResNet? 224, yes, 224. And if we resize the document to the page to this resolution, of course, all these characters will be illegible. So this is another the direction of research, how to work with high resolution images. Yep.
Or native image recognition ones.
I have this classification just in few slides, and mini GPT-4 is using so-called deep fusion. So let's maybe answer this question after one slide. And the last benchmark I want to mention, so previous benchmarks are called static benchmarks, but there is also another benchmarks that are called arenas. And in arenas, you can run multiple models on the same task. So for example, here there is model A, model B, and you can run multiple models, and people will just choose if both models are best. There's no option both are great. A is better. Oh, well, but it doesn't say that they did a good job, maybe. So, there are different arenas where you can do this labeling. And it's interesting that I know that several models, they use GPT-4 model for labeling instead of real people, because there was a research that correlation between people's preferences and GPT-4 it's called ranking. They have high correlation, and for example, the model Vicuña, which is large language models, it was trained on the reward model was actually trained on the answers from ChatGPT. And the same for visual models. I don't remember which one was trained on GPT. Oh, I believe there was a data set created based on the GPT-4 model classification. So how can we combine different modalities? There are two approaches. The early approach, which is called not early fusion, the early approach was deep fusion. When people tried to incorporate the information from other domains inside the model, for example, applying cross attention or creating custom layers. And these are examples. If you want to run Flamingo, I uploaded the code for this week. You can just run this model, but you should run this on Colab, oh, sorry, on Kaggle, because Kaggle has larger space, so it won't be running on Colab. So if you want to run this Flamingo model, you should run it on Kaggle or apply some quantization. So the custom layers, you remember we talked about gated attention, so these are called custom layers. They're used in these models like Lava and GPT-4 and Gemini. And more recent integration of different models, they use so-called early fusion, when we don't change the model, but we perform a pre-processing of our images into tokens, and there are two subgroups, non-tokenized and tokenized. So, okay, did it answer a little bit about the question about how GPT-4 reads the images? So now let's talk about actually two, I can't say the most recent models, because currently diffusion, like stable diffusion models, they don't use, well, they still use visual transforms, but this year there were a lot of papers that were trying to avoid this quantized variable autoencoder, to avoid the quantization, because when we quantize the information, then we have some distortions, and the reconstruction then is not in some cases pretty realistic. But still, let's talk about a very important model, which is called vision transformer. We talked about transformer models in NLP, and it's interesting also historical perspective. First, in the beginning of our course, we used convolutional neural networks which came from images. now images borrowed the autoregressive model from language models. So, and the model that uses transformers autoregressive models for images is called visual transformer. So, as David said, that classical resolution is 224 by 224 pixels, and they cut these images into patches of shape 16 by 16 pixels, 16 by 16. And as the result, from one input image, you will get 14 times 14 patches. So if your image was 224 by 224, then every page is 16 by 16, and the number of pages will be 14 squared, which is 196, if I'm not mistaken, 196 pages. After that, we need to create tokens from pages, and which methods to convert a small image into a vector, which neural network layers can we use for that?
Using convolution.
Convolution. Yes, we can use so convolution, but the convolution, so it's another idea, but convolution we should apply to the original image then, because when we convolve the filter of size 16 by 16, actually we will get one number for one page. So this is a good idea to use convolution. And for example, if we want to create a vector of shape D, then we will need to apply D convolution filters. But if we have patches, then it's easier just to flatten them and apply a linear MLP, just multilinear perceptron, one or two layer perceptron. So we will get a vector embedding for every patch. After that, we want somehow to understand the position of these patches, like a relevant position. For example, is this was this page in the bottom of the image or on the top? So for this reason, we should use also positional embeddings. But there is also one problem if we use an image of with another resolution. Then the page with index, so typically we label from the top to the right, so 1, 2, 3, 4, 5, and so on. So the page, for example, with index 5, which was in the bottom of the image, or image with higher resolution, may end up on the top. We will talk about how to solve this problem later. For now, let's assume that all images have the same resolution. And after that, we pass these tokens through transformer. Again, there are several layers, several heads, the same transformer model as in LLM. And because what was the year? It's not it's not far away. So 21. I want to say that at that time people just wanted to work on classification of images, but it wasn't. So it was just 4 years ago. So they also used kind of CLS token, classification token, to train this model. And they trained the loss function was cross entropy loss. So they wanted just to predict the class, the label of the image. Like, what is that, landscape, or I don't know, a child or a tree and so on. So they used only this token in their loss function. But as you remember, transformers, they have output tokens as well. So for every input embedding, after self-attention, we also have the output embeddings. And even though the gradient was going only through the first token, through the head, through CLS token, those embeddings were also trained. And now we will talk about next model, CLIP, which actually used this kind of context, but in this case, context is image context-aware embeddings, not only the classification token. Okay, so the next modification of this model, okay, before going to CLIP, there is just visualization. So do you have any questions about the architecture? So it's pretty straightforward if you are familiar with transformer in large language models. Again, it's kind of BERT model. Erase the drawing. Okay, on the next slide, I just provided some a visualization of the attention mechanism in this visual transformer. So if you look at the attention with CLS token, you can find the tokens that had higher attention score. Every token corresponds to a patch, not to one pixel, but to a patch. But patch in this patch can be 16 by 16 pixels. In the other example, it's 8 by 8 pixels. And looking at these attention with CLS token, you can actually build this heat map, which will visualize which area on the picture was more important for this classification. If you think about project on you remember there was a paper, attention is all you need. In this paper, they also built, but it was kind of pixel-wise attention, which pixel was important for the image captioning. So now you can understand the idea. You can train the visual transformer, you can have the GPT parts and use cross attention. And cross attention will tell you which part of the image was important for the specific token in your text. So then we can visualize the different heads of our transformer. And like in NLP, you remember different heads learned different kind of aspects of language. Here they also demonstrate like they visualized three heads, so three colors, and you can see that a different head kind of captures the information about one object or one specific object. But it's just interesting fact. So some comparison, if we take a small data set like ImageNet, then transformer models, they work worse than ResNets. So this ViT, this is the modification of ResNet. But when the size of data becomes much larger, then finally transformers outperform the classical convolution neural networks. Okay. I have some more illustrations about what they learn. So if we look at the pages 16 by 16, you can learn first principal components and visualize those components, and you will see that different embeddings in this visual transformer, they learn different patterns like in convolutional neural networks, different kind of Gabor filters and so on. It's interesting to look at the positional embeddings. You can see that positional embeddings, they kind of correlate with the true position of the patch. Like here we have values in the bottom, here we have high values on the top. And now I can tell you about how to work with different resolutions. So if you have an image with high resolution, for example, twice larger, then you can use these positional embeddings and interpolate them, like add up and divide by 2 to get the embeddings for intermediate tokens. So this is how we can use this model for different resolution images. And finally, it's interesting to look at the attention on different layers. So on the shallow layers, it's interesting that every patch can be connected with close patches or with patches on a large distance. So this is the distance between patches. But and it's impossible in convolutional neural networks, because in convolutional neural network, you remember, the receptive field is just around the current pixel area. So for convolutional neural networks, we wouldn't see any relations with like other pixels, in this case patches. And as in large language models, you remember, like deeper layers, they learn more general semantics, and the same is with visual transformers. For deeper layers, our patches actually look at, or in average, they look on the more distant patches. It's interesting information. Okay, finally, let's move to a slight modification of this transform model, which is called CLIP, and which is used in particular in stable diffusion. And I think I will talk about stable diffusion because we have time next next class about VAE and on Friday about diffusion models. So again, the same architecture, images, split it into patches, but now the embedding of the image, so this CLS token, you can think about this as embedding of the entire image, is not used for classification, but it's used for alignment with text. So you have a data set with images and texts, and you want to train a model that will align the text embeddings. So here we have two transformer models. One text, like a ViT model that returns text embedding, and image transformer model that returns image embedding. So it wants to train these two models, two transformer models, such that text that corresponds to a specific image after passing through text encoder and image through image encoder, the embeddings are very similar. So they have higher dot product. And this is the illustration. So we take n pairs text and images. We pass this n text through encoder for text. We pass this n images through encoder for images. As the result, we have n plus n to n embeddings. And then we can construct this all possible dot products, like embedding from our first pair for text times embedding from our first pair for image, then embedding from the first pair for text times embedding for this image embedding for the second image, and so on. And the goal is to maximize the diagonal, to maximize the dot products between the image and text that were related, where text somehow describes the image. And this is the loss function. So we want to maximize the diagonal, and we want to minimize the off-diagonal dot products. And this model used a lot of data and a lot of computational resources. Nowadays, you can train this model on one node with 800 GPUs. But at that time, we used 500 video cards. So yeah, the difference with our previous ViT transformer model is that in the loss function, in ViT transformer, loss function was cross entropy based on the class. In this case, the loss function is if you look at this expression, it's just a softmax. It's just softmax. Softmax returns the probability, and we want to maximize the probability of the class with the same inputs. That's the point. Later, there was a slight modification of CLIP, which is called 6-lit. I think it was from OpenAI. I don't remember. So the only difference in this paper was that they proposed to approximate the softmax loss function with binary cross entropy, with binary classification function. So what is it helps to avoid keeping track of the data for the entire batch. For example, if you train on different nodes, then you should aggregate the responses from all the nodes to calculate this denominator, the sum. In case of this loss function, we perform binary cross entropy. In other words, we want to maximize the corresponding classes, and it will be our class 1. And if vectors belong to different classes, we'll force the model to classify as class 0. And this helped to train the model much faster. And so when you hear CLIP, sometimes so it doesn't mean that it's the original CLIP model. Maybe it was actually SIG-LIP model. Okay, and if you look at the code for this Flamingo model that I uploaded, so I just uploaded some images from Coco dataset, and we can create the prompt. So you can see we upload the CLIP CLIP model for embeddings for images, and we can create a prompt. A prompt as follows, like image token, then text. They used end of chunk token to separate images, then second images, and then image and unfinished prompt. It's kind of a few short prompt engineering. So we say that the first image is the image of Cass, the second image is the image of Sync, and the third image, and then just we ask our model to continue generate, and it, in my case, the response was it's an image of a Buffett table. Okay, so I hope it gives you some idea about how we can convert images into vector embeddings. I think I will talk about more recent models and details. I think it's more interesting to talk about a stable diffusion model, how we can generate images from prompts, because it's kind of as again, it may change in 1 year, but for now it's kind of the most popular model Flux. Okay, yeah, that's it for today.